All right, let's take a look at the practice test. For the instructions, we're asked to find the unit vector u in the direction of the vector v. So for the first problem, we're given our vector v, and it's written as a linear combination of our unit vectors I and j. So we have to be comfortable with this notation because it's going to come up pretty often in math. So the vector v is equal to -4 times the unit vector I plus 8 times the unit vector j. So when you see a hat like that, that's telling you have a unit vector or a vector with a magnitude of 1. So what I'm going to do is use a little simple formula. My goal is to find a unit vector u, so let me just write that. And basically it's going to have the same direction, or you can think about that as the direction angle, as this vector v, but the magnitude is going to be 1. So the formula is very simple. You just take your vector v, and you're going to multiply it by 1 over the magnitude of that vector v. So essentially, it's just going to scale it down to the point where it has a magnitude of 1. That's what you're trying to find, but the direction angle would be the same. So looking at this guy, remember how this notation works? If you want, you can write this in component form. So the horizontal component is going to be -4. It's what's multiplying that unit vector I. The vertical component is 8. It's what's multiplying that unit vector j. And so you can say that this is -4 and then 8 for the components times, we'll have 1 over, what's the magnitude of my vector v? Let me write that over here. So the magnitude of my vector v is the principal square root of, you have your horizontal component squared, -4 squared is 16, and then plus your vertical component squared, so 8 squared is 64. If we do 16 plus 64, that's going to give me 80. And of course, you could break 80 up into 16 times 5. So 16 is a perfect square, so this is going to be 4 times square root of 5. So 4 times square root of 5. So let's write that like that. Let's scooch down a little bit, and let's just say that this is equal to. You could put this out in front if it's more comfortable for you. So let me write 1 over 4 times square root of 5. And then times, you have this vector here with -4 and then 8 as the components. So let me slide down here a little bit. And so this guy is going to get multiplied by each. So essentially you're going to have -4 over 4 times square root of 5. Let me put my bracket in there. And then you're going to have 8 over 4 times square root of 5. Okay, so let me put that like that. And let me come down here a little bit. I'm going to do some canceling. So this would cancel with this, and this would cancel with this and give me a 2. Let me write a 1 up there. So let's say that this is -1 over the square root of 5. Let me put my bracket in there. And this is 2 over the square root of 5. Now, a lot of times with these problems, you'll see people not rationalize the denominator. That's not something I'm really comfortable with. So if your book does this, then that's fine. I'm just going to take the extra step and rationalize the denominator. Let me actually slide this down here. So times the square root of 5 over the square root of 5. And let me do times the square root of 5 over the square root of 5. Let me close that down. And so this would give me, let me put my brackets in here. You have negative square root of 5 over 5. And then you have 2 times square root of 5 over 5. So this right here would be your unit vector u. So in other words, the magnitude is 1, and you can check that really easily. And it has the same direction as the vector v. So in other words, the direction angle is the same, and you could check that as well. Now, the way I've written it here is in component form. We were given our problem as a linear combination of the unit vectors I and j. So typically, you want to stick with the notation you were given. If you're given the problem in component form, answer in component form. If you're given the problem as a linear combination, answer as a linear combination. So what I'm going to do is just convert this over. I'll say this is equal to this right here. This negative of the square root of 5 over 5 is just going to be multiplied by the unit vector I. And then you're going to have plus this guy right here is going to be 2 times square root of 5 over 5. That's going to be multiplied by the unit vector j. So again, this would be your component form, and this would be your linear combination of the unit vectors I and j. All right, let's take a look at problem number 2. So here we have our vector v. It's given to us in component form. So the horizontal component is 30, and the vertical component is 40. Now, if you want to get some practice, again, you can just go back and forth between the two forms. So you can do a linear combination of the unit vectors I and j. So you could say this is 30. That's your horizontal component. That's going to be multiplied by the unit vector I, and then plus this is 40. That's your vertical component. That's going to be multiplied by the unit vector j. So again, just two different ways to write things. Now, if you want to find the unit vector u again, that just means it has a magnitude of 1, in the same direction as this vector v, meaning the direction angle is the same, you're just going to take this vector v, so let me write this as 30 and then 40 for the components, and you're going to multiply it by 1 over the magnitude of that vector v. So what is the magnitude of the vector v? Well, again, you just take the square root of your horizontal component squared plus your vertical component squared. This might be something you want to key into a calculator because the numbers are pretty big. Let's just see what this is going to give us. So the result I get is going to be 50. And where that comes from, 30 squared is going to be 900. 40 squared is 1600. 900 plus 1600 is 2500. And if you take the principal square root of 2500, you get 50. So let's put 50 down here and let's slide down and we'll just do our multiplication. Again, this is going to be multiplied by each guy here. You can put it out in front. I think that makes people feel more comfortable. So 1 over 50, that's your scalar. And then these components, you have 30 and then 40. So let me make this bracket a little bit better here. And I'll just slide down here. Maybe I'll just bring the equals over here. So this would be 30 over 50, like this. And then this would be 40 over 50, like this. And of course, you can simplify that. So you can say that this guy right here is going to be 3/5, just canceling a common factor of 10. And this guy right here would just be 4/5, again, canceling a common factor of 10. So we write it like this in component form. We were given that guy in component form. But again, if you just want to practice, you could write this as a linear combination of the unit vectors I and j. So you could say this is 3/5, again, that's your horizontal component, multiplied by the unit vector I, then plus 4/5, that's your vertical component, multiplied by the unit vector j. All right, for the next few problems, the instructions are going to change. Now we want to find the dot product, some people call this the inner product, of the vectors u and v. All right, so for problem 3, we have this vector u given to us in component form. So the horizontal component is -8, the vertical component is -3. Then we have this vector v, also given in component form. The horizontal component is 6, and the vertical component is also 6. So if you want to find the dot product, you would say this vector u, and then dot this vector v. All you're going to do is start by multiplying the horizontal components together. So in other words, -8 times 6. Then you're going to go plus. You're going to multiply your vertical components together. So -3 times 6, like this, and that's all it is. It's a very, very simple process. So we would say that -8 times 6 is -48, and then plus -3 times 6 is -18. So -48 plus -18, that's going to give me a result of -66. So that would be my dot product of this vector u and this vector v. All right, let's take a look at problem number 4. So here we have our vector u. So this is written as a linear combination of the unit vectors I and j. So we say this is equal to -9 times the unit vector I minus 2 times the unit vector j. So similarly here, this is a linear combination as well. So this vector v, this is going to be equal to -3 times the unit vector I minus 8 times the unit vector j. All right, so if we want to find the dot product, let's go ahead and say this vector u and then dot this vector v. Again, I'm going to multiply the corresponding components and then sum those guys together. So what I mean by that is you're going to take these horizontal components. So this is -9 times -3. And then I'm going to add this to, I'm going to take these vertical components and multiply those. So -2 times -8. Maybe I'll wrap this one for clarity. When you get negatives, it gets a little busy. All right, so let's say equals here. -9 times -3 is going to be 27. And then basically you're going to have plus -2 times -8. That's going to be 16. And then 27 plus 16, that's going to give me a final answer of 43. So that's my dot product of this vector u and this vector v. All right, for the next problem, the instructions are going to change a little bit. We want to find the measure of the angle theta between vectors u and v geometrically. So looking at problem 5, we see we have this vector u given in component form. So the horizontal component is 8 and the vertical component is 3. Let me actually just write this here. So for the vector u, we have the horizontal component of 8 and the vertical component of 3. And then for the vector v, this is also in component form. So the horizontal component is 2 and the vertical component is 7. Okay, let me grab this real quick. And I'm just going to paste this in here. Before I start working with this sketch, I want to show you something. In the lesson, we looked at this formula here, but we didn't talk about where it came from. I just mentioned that it was from the law of cosines, but I want to show you this on an example. So the cosine of theta is equal to, you have the dot product of this vector u and this vector v, and this is over the product of these two magnitudes, right? So the magnitude of this vector u times the magnitude of this vector v. If you're using a textbook, you'll probably see a sketch like this. And basically, this is how you can derive this guy. You're going to use the law of cosines. So you're trying to find this angle here. Remember, with the law of cosines, you have this angle and the side opposite that are related, right? So something like, let's say a squared is equal to b squared plus c squared. And then we could say minus 2 times b times c times the cosine of that angle a. Okay, so something like this. Now let's go back up and let's think about this. So first off, you'll notice that this vector u and this vector v, they're both in standard position. So the initial point is at 0, 0 for each. Now for the vector u, the terminal point is at 8, 3. And then for the vector v, the terminal point is at 2, 7. So far that's pretty easy to understand. Now, this is where it gets a little bit tricky. You'll see that this vector here is denoted with the vector u minus the vector v. So if I had the vector u minus the vector v, that would be what? Well, I would subtract 8 minus 2, that would give me 6, and then 3 minus 7, that would give me negative 4. Okay, so this 6, negative 4 here, as a terminal point, if I started at the origin, would look something like this. So I'd go 6 units to the right, and then 4 units down, so it would be like this, and I would sketch this guy as something like that. Okay, so essentially what's happening is I'm taking this guy and I'm just shifting it here to where the initial point is now at 2, 7, and the terminal point is going to be at 8, 3. Okay, you can see that from 2, I would basically just be adding 6, so I'm going to the right by 6 units to get to 8. And then from 7, I'm subtracting 4 units away or adding negative 4, so I'm dropping by 4 units to get to a y location of 3. Okay, so that's all I'm doing. I'm just shifting this over here, and that allows me to complete this triangle. Okay, so now that we know where all this stuff is coming from, let me get rid of this. Essentially, you're just going to use the law of cosines. Before we use the law of cosines, we have to know a few things. So what is the length of this vector here, or the magnitude? So the magnitude of this vector u minus this vector v. How do we figure that out? Well, we can just use the regular distance formula because this point is 2, 7, and this point is 8, 3. This is the initial, this is the terminal. Okay, so we can say this is the square root of, you take your x sub 2 minus your x sub 1 quantity squared plus your y sub 2 minus your y sub 1 quantity squared. Okay, so in this case, let's just say this is 0.2 and this is 0.1. Again, you can reverse it, it won't matter. But let's erase this and just say that this is going to be 8, and then this is going to be 2. And then for this guy right here, this is going to be 3, and this is going to be 7. Now, what you're noticing here is we're getting 6 and negative 4, which is exactly what we got when we did our subtraction, right? So this is going to be 6 squared, or 36. And this right here is going to be negative 4 squared, or 16. So 36 plus 16, that's going to be 52. And you could write that as 4 times 13. So this would be 2 times the square root of 13 if you simplified it. Then we also need the magnitude of my vector v. So that's pretty easy. Again, the terminal point here is 2, 7. So it's the square root of 2 squared, which is 4, plus 7 squared, which is 49. 4 plus 49 is 53. So this is just the square root of 53. And then you'd have the magnitude of the vector u. So this is the principal square root of, you're going to take 8 squared, which is 64. And then plus 3 squared, which is 9. So 64 plus 9 is going to be 73. So this is the principal square root of 73. Now that we have this, let's go through and use the law of cosines. I'm just going to grab this real quick, and I want to paste this right here because we're going to need it in a moment. Let me actually drag this over so it's a little bit more in line. We're going to come back up here. So let's start out by taking the magnitude of this vector u minus this vector v. This would be squared. This would be equal to the magnitude of the vector u squared, and then plus the magnitude of this vector v squared. And then you would have your minus 2 times the magnitude of the vector u times the magnitude of this vector v. And then lastly, you're going to have times the cosine of that angle. Again, that's what we're trying to find, that theta there. Okay, and I know this is going on multiple lines here, but we'll clean this up in a moment. So again, you can see that if you related it back to what we already talked about, let's say you had this guy as a and this guy as angle A. So this would be a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of a. So it's just the law of cosines. It's just rewritten. Again, for the side lengths here, you're using the magnitude, right? So this is a length that has the magnitude of the vector v. This has a length that's the magnitude of the vector u. This has a length that's the magnitude of the vector u minus the vector v. So that's all it is. Okay, so let's get rid of this, and let's grab this real quick. And let me paste this in here. And I'm just going to do a lot of cleaning up. So let's try to write this in line. So we have the magnitude of the vector u minus this vector v, and this is going to be squared. And this is equal to, we have the magnitude of the vector u being squared plus the magnitude of the vector v being squared. So let me get rid of this part right here. And I'm going to actually slide this down. And we can get rid of this border now if we want. And then I'm just going to actually move this up here. Don't need to rewrite it, so it all fits on one line. Okay. Let me put my border back in here. So if I squared this guy, this is 2 times square root of 13, okay? So this is 2 times square root of 13, and I'm going to square that guy. And this equals, this guy right here is the square root of 73, and I'm going to square that guy. So let me write the square root of 73, and I'm just going to square that. And then plus, I'm going to have my square root of 53, and that's going to be squared. So that's coming from the magnitude of the vector v being squared. And then I'm just going to go minus 2 times, again, the magnitude of the vector u is the square root of 73. And then the magnitude of the vector v is going to be the square root of 53. And then lastly, it's times the cosine of my angle theta. Let me get rid of this. And actually, you don't need that anymore. It's just basically calculations at this point. And let me rewrap that and slide this down here like this and slide this up here like this. So for this one, 2 times square root of 13 being squared, 2 squared is 4. And the square root of 13 being squared is 13. So 4 times 13, that's going to give me 52. And this equals the square root of 73 squared is 73. And then plus the square root of 53 squared is 53. And then minus 2 times the square root of 73 times the square root of 53 times the cosine of theta. So you want to solve this for the cosine of theta. And to do that, I would say 73 plus 53, that's going to be 126. So let me write that in there. And I'll say 52 minus 126, that's going to be negative 74. So this becomes negative 74 is equal to negative 2 times the square root of 73 times the square root of 53, and then times the cosine of theta. Now again, if I want to solve for the cosine of theta, I'm just going to divide both sides of the equation by negative 2 times the square root of 73 times the square root of 53. So let me do that over here as well. So let's go negative 2 times the square root of 73 and then times the square root of 53. Okay, so this is going to cancel, and I'm going to write this cosine of theta on the left. So let's say the cosine of theta is equal to, so you have negative 74 divided by negative 2. So let's go ahead and do that on the calculator, and I get 37. So let's say this is 37 over the square root of 73 times the square root of 53. Now let's stop for a moment. Before we calculate this, I want you to remember the formula that we had. The cosine of theta is equal to, you had the dot product of the vectors u and v. Let me make that v a little bit better there. And then over the magnitude of u times the magnitude of v. What's the dot product of these guys? So u dot v. What is that going to be equal to? Well, you have 8 times 2, that's 16. And then plus 3 times 7 is 21. 16 plus 21 is going to be 37. So coming back, notice that's what you have here, the dot product of u and v. Now what about this? Well, the square root of 73 is the magnitude of the vector u, and the square root of 53 is the magnitude of the vector v. So here you see that you came up with your formula. Now if you wanted to do it with that generic sketch, you can. That's one way to prove it. But I think that doing it with an actual example is a little bit easier to comprehend, and also it makes the math a little bit more manageable. Okay, so at this point, all you're going to do is say that theta is equal to the inverse cosine of this guy right here, so 37, over your square root of 73 times your square root of 53. Let's key that into the calculator and just try to be extra careful when you enter this in. You're going to get about, let's say 53 point, let's go ahead and say 5 degrees. So that would be the angle between the vectors u and v. All right, for the next few problems, the instructions will change. Now we want to find the measure of angle theta between vectors u and v. So for problem 6, we have our vector u given in component form. So the horizontal component is 2, and the vertical component is negative 4. Then we have our vector v also given in component form. So the horizontal component is 4, the vertical component is -5. So remember our little formula here. It's not that tough to remember. Maybe you have to write it down a few times. So the cosine of theta is equal to, you're going to have the dot product of these two vectors. So u dot v, like this. This is over. You're going to have the magnitude of your vector u times the magnitude of your vector v. So first I'm going to figure out the dot product of the vectors u and v. So to do that, again, we'll go u dot v. This is equal to, you're going to multiply the horizontal components together. So 2 times 4 is going to give me 8. And then plus, multiply the vertical components together. So -4 times -5 is 20. So 8 plus 20 is going to be 28. So this right here is going to be 28. Very easy. Now, for the magnitude of the vector u, this is going to be what? The square root of, you take 2 squared, that's 4, and then you add that to -4 squared, that's going to be 16. So this would be the square root of 20. Now this would break down into 4 times 5, and so this is 2 times square root of 5. So 2 times square root of 5, so let's write that right there. This is 2 times square root of 5. And then for the magnitude of the vector v now, this is the square root of, again, you take 4 and square it, that's 16, and then plus -5 squared, that's going to be 25. So 16 plus 25, that's going to be 41. So this right here would be the square root of 41. Okay, so thinking about this, you could just key this into your calculator and say that theta is equal to the inverse cosine of, you can go 28 over. Now you could multiply this together. 5 times 41 is 205, so you could say this is 2 times the square root of 205. It's not necessary, but it might make it a little bit easier to punch it into your calculator. Again, that's really personal preference. So this is approximately what? Let's just key it in. And I get about 12.09, let's say, degrees. I'll just round it to the nearest hundredth. Again, if you're having problems when you punch this into your calculator, you get something like a domain error, make sure you wrap things in parentheses for clarity. Some calculators are good about it, and other ones you really have to be specific. So for the angle between the vectors u and v, we get about 12.09 degrees. All right, let's take a look at problem 7. So here we have the vector u, which in component form has a horizontal component of 2 and a vertical component of 9. And then we have our vector v, which in component form has a horizontal component of 8 and a vertical component of -3. So again, it's just a little simple formula. Let's just go ahead and say that the cosine of theta is equal to the dot product of these vectors, so u dot v, and this is over the magnitude of u times the magnitude of v. So let's figure out what is the dot product first. So u dot v is equal to what? So I'm going to multiply these horizontal components together. So 2 times 8 is 16. And then plus, I'm going to multiply these vertical components together. So 9 times -3 is -27. So 16 plus -27, that's going to give me -11. So let me put this up here as -11. Let me get rid of this. And now we're going to think about the magnitude of the vector u. Again, that's the square root of 2 squared plus 9 squared. So 2 squared is 4, plus 9 squared is 81. So this would be the square root of 85. Now 85 divided by 5 is 17, so you really can't do anything with that. So this would just be the square root of 85. And then for this guy, we want the magnitude of the vector v. So this is going to be what? It's the square root of 8 squared, which is 64, plus -3 squared, which is 9, and 64 plus 9 is going to be 73. So this would be times the square root of 73. Let me make this 3 a little bit better here. All right, let's get rid of this. Now, again, you could punch this in your calculator like this, or you can multiply 85 times 73, and you would get 6,205. So this would be the square root of 6,205. Let me make that a little bit better there. So in your calculator, let's say that theta is equal to the inverse cosine of this guy right here, so -11 over the square root of 6,205. Again, be very careful about how you key this in, because you might get a domain error if you're not specific. If I round to the nearest hundredth, I get about 98.03 degrees. So that's going to be the approximate angle between these vectors u and v. All right, let's take a look at problem number 8 now. So here we have our vector u. This is now written as a linear combination of the unit vectors I and j. So we have the negative of the unit vector I minus 3 times the unit vector j. And then for the vector v, it's written in the same way, so as a linear combination. So here, this is equal to 3 times the unit vector I plus 8 times the unit vector j. So again, the formula is the same. So we have the cosine of theta is equal to, you're going to have the dot product of your vector u and v over the magnitude of u times the magnitude of v. So let's start with this dot product here. Again, you can write this in component form if you're more comfortable. You can put a little -1 there if that helps you out. So the dot product of u and v, so u dot v is equal to what? So -1 times 3, that's -3, and then plus -3 times 8, that's going to be -24. So this would end up giving me -27 as a result. So let's put this up here as -27, and let's get rid of this. Okay, the next thing is you want the magnitude of u and the magnitude of v. So what is the magnitude of u? Well, I just want the square root of, again, this is your horizontal component, so it's -1, and I'm going to square that, plus this is your vertical component. Make sure you take that minus with you. You can always go plus negative if you're having trouble with that. So this is going to be -3. That's going to be squared. So -1 squared is 1, and then -3 squared is 9. So this would be 1 plus 9, which is going to be 10. So this is the square root of 10, and we can just write that in right there, like this. And then we want the magnitude of the vector v. So again, the square root of, you've got 3. You're going to square that, you get 9. And then plus, you've got 8. You're going to square that, you get 64. And so 9 plus 64 is going to be 73. So the magnitude of the vector v is going to be square root of 73. Okay, let's get rid of this. And let's think about this. So you could punch this into your calculator again as is, or you could multiply first. So you could say this is the square root of 730. And so let's go ahead and say that theta is equal to the inverse cosine of -27 over the square root of 730. Close that down. So this is approximately, I get about 177 point, let's say 88 degrees, if I round to the nearest hundredth. So the angle between my two vectors u and v is going to be about 177.88 degrees. All right, let's take a look at problem number 9. So here we have our vector u, which is written as a linear combination of the unit vectors I and j. So this equals -3 times the unit vector I plus 5 times the unit vector j. And then our vector v, again, written as this linear combination of the unit vectors I and j. So it equals 3 times the unit vector I minus 8 times the unit vector j. All right, so once again, we would just think about our simple little formula. The cosine of theta is equal to, you have the dot product of u and v. So let's just do this on the fly. So we know this is -3 times 3. That's going to be -9. And then plus, you have 5 times -8. Again, always take this sign with you. So 5 times -8 would be -40. So this right here would be -9 plus -40. That's going to be -49. So that's your dot product for u and v, those two vectors. Okay, this is over the magnitude of u. So for that one, it's going to be the square root of, you have -3 squared, which is 9, and then plus 5 squared, which is 25. So 9 plus 25 is 34. So this is the square root of 34. Now 34 is 17 times 2, so you really can't do anything with that. The other guy is the magnitude of the vector v. So this is the square root of, you have 3 squared, which is 9, and then plus -8 squared is 64. And we know 9 plus 64 is going to be 73. So this would be the square root of 34 times the square root of 73 down here. Again, you can key this into your calculator, or you can say 34 times 73. That's going to be 2,482. So you can just say this is the square root of 2,482 down here. In my calculator, I'll say theta is equal to the inverse cosine of this guy right here, so -49, over the square root of 2,482. Close that down. So this is approximately, if I round to the nearest hundredth, I get about 169 point, let's say 59 degrees. So my angle between the vectors u and v would be about 169.59 degrees. All right, for the next few problems, the instructions tell us to determine if the vectors u and v are orthogonal. So what that means is basically that you have perpendicular vectors, or the angle between the vectors is going to be 90 degrees. So thinking about the formula for the angle between two vectors, so the cosine of theta is equal to, again, you have the dot product of this vector u and this vector v, so u dot v like that. And then this is over the magnitude of the vector u, and that sort of looks like a v, so let me clean that up. and then times the magnitude of the vector v. So what happens is, if you have orthogonal vectors, the angle theta is going to end up being 90 degrees, right? So those guys will end up being perpendicular. So that happens when this guy right here, this dot product, is 0, okay? Because this will be 0 over something that's not 0. So you get 0 as a result there, and basically your theta there is going to be 90 degrees. Okay, so thinking about this, we have our vector u in component form. We have a horizontal component of -5 and a vertical component of -2. We have our vector v in component form. We have a horizontal component of -2 and a vertical component of -5. So if we do u dot v like this, again, all we're going to do is multiply the horizontal components together. So -5 times -2, that's +10. And then plus multiply the vertical components together. So -2 times -5, that's going to be +10. So this becomes 10 plus 10, which is 20. So that's not 0. So we can just say no. These are not orthogonal vectors. Okay, let's take a look at problem number 11 now. So again, we want to determine if they are orthogonal vectors. So here we have our vector u written as a linear combination. So this is going to be equal to 9 times the unit vector I minus 4 times the unit vector j. Then we have v that's also given as a linear combination. So this is equal to -8 times the unit vector I minus 18 times the unit vector j. Okay, so the first thing we would figure out is, what is the dot product? So we're going to go u dot v like this. So you're going to multiply this guy right here. So the horizontal component is 9 times the horizontal component here, which is -8. So 9 times -8 is -72. And then plus, here I'm going to go plus negative and plus negative, so I don't make a sign mistake. So your vertical components would be multiplied together. So -4 times -18, that would be +72, and so this is 0. So this tells me that yes, we do have orthogonal vectors. And again, you can just plug into the formula and see that the angle between the vectors would be 90 degrees. So cosine of theta is equal to, this would be 0 here. So this leads to saying that theta is going to be equal to 90 degrees. So we know that these are orthogonal vectors.